Work it, make it, do it, make sense.
So thanks for coming to my talk about about how to maintain data consistency in a microservice architecture. So in the talk, I'm going to cover sort of three topics. First, I'm going to explain why there is a problem with maintaining data consistency in a microservice architecture. There's actually problems with doing querying as well, but that's sort of like a whole separate talk. I'm going to explain why the traditional distributed transaction mechanism, two-phase commit, XA, whatever you want to call it, is not really an option in a microservice architecture. And I'm going to show how this concept of a saga, which is actually a concept that was first showed up in a paper back in 1987. That was kind of the title of the paper, was Sagas. How that is a good transaction model for applications that you're building with the microservice architecture. So those are the three topics. But before getting into that, I want to talk a little bit about me. So if you don't know me, obviously Chris Richardson. I live in the San Francisco Bay Area, though I actually grew up in Cornwall, but I appear to have lost my accent along the way. And yeah, it meant that I flew here on an American airline, so I sort of risked not having a seat. And apparently I might not be able to take my laptop back, if the news stories are to be believed. Anyway, so yeah, I live just in a city called Oakland, where I can sort of see San Francisco from my house. Got my start in programming back in the mid to late 80s building Lisp systems. So everything from sort of the runtime, garbage collector, compilers, all the way up the stack. Lisp, of course, being an early functional language. Then it became object-oriented. Eventually programmed in Java, wrote the book Pojos in Action. It's all about Spring, Hibernate, which 10 years ago were revolutionizing how we did enterprise Java development. Started tinkering with this obscure service known as Amazon EC2, which is pretty much before the term cloud computing, or at least I don't think I'd heard about the term cloud computing back then. And created Cloud Foundry that was a PaaS for deploying Java applications on EC2. And then that got acquired by SpringSource back in 2009, right before SpringSource was acquired by VMware. So I was part of SpringSource, VMware, and then Pivotal for 4+ years. And since then, that was 3 years ago, roughly. Since then, I've basically been focusing on the microservice architecture. So I do consulting and training, and feel like I spend my time flying around the world to get from one consulting or training gig to another. And then I'm also working on a startup, and we're building a platform to simplify the development of transactional business applications that use the microservice architecture. So in fact, many of the concepts that I'm talking about today actually relate back to what the startup is doing. And then I'm also writing a book called Microservice Patterns that is out, like the first 4 or 5 chapters are out in Manning Early Access program. So if you want to know more about that, go to learnmicroservices.io, where there's links to the book, links to articles, links to code, videos, everything you need to know about the microservice architecture. So here's the agenda. First, kind of want to talk about why our ACID transactions, something with which we're very familiar and love, is not really an option in a microservice architecture, or at least not when you have transactions that span multiple services. Within a service, you can obviously use ACID transactions, but not between them. And that's when sagas come into play. So, obviously most of the talk is about that. What are sagas? How to kind of implement them, some kind of design considerations. Then I'm going to finish by talking about how the sort of the underlying foundation for sagas is this sort of transactional messaging mechanism. So you can imagine that in your architecture, your services collaborate primarily by exchanging messages, which is sort of interesting given that there's so much talk about using REST and so on. Okay, so that's the agenda. Let's get going. So imagine that you're working on an online store. And actually, maybe it's sort of a B2B kind of online store, because perhaps customers have a credit limit. And so, very basic idea, namely that if you added up the open orders, the order totals for all of the open orders, then those orders cannot exceed the credit limit. That's like kind of a golden rule in the system. It's an invariant that must never, ever be violated, right? You can never allow a customer to place an order that will cause that credit limit to be violated. And really simple, right? And it seems simple because we're pretty much used to building monolithic applications. And so, in a traditional architecture, you just make one of your service, you make the appropriate service method transactional. So, if you're using the Spring framework, you stick an annotation on it, or in some other framework, you begin a transaction, do what you need to do, and then you commit the transaction. And then during that transaction, you just access the data that you need. So you go you go to the order table, and you find the existing orders, you go to the customer table, and you make sure that everything works, and then you create a new order, and you commit the transaction. And it's really simple. So, the SQL that you end up executing would look something like this, right? Find the existing orders, find the credit limit, make sure that the total doesn't exceed the credit limit, insert a new order, and commit. Really, really simple. I mean, that's the kind of thing that we do in our applications without really thinking about it. That's because we're just so used to the ACID programming model that gives us certain guarantees. In particular, it means that if there are concurrent transactions that attempt to create orders for the same customer, the properties of ACID transactions will guarantee that that invariant is never violated. Conceptually, these transactions get executed one after another. Now, you know that if you're familiar with the intricacies of isolation levels, there's a whole bunch of fine print associated with what I just said that makes it potentially a little more complicated than that. But at least given the classic definition of ACID transactions, this is brain dead simple, in a monolithic application. But the problem, as we know, is that sort of monolithic applications sort of have a habit of growing. And they have, over time, they just get bigger and bigger and bigger. At least the successful ones, right? If you're unsuccessful, the company dies and the application you stop developing it. But, successful monolithic applications, given enough time, will become these huge monoliths. And they get to the point where any notion of agility becomes impossible. And you're in this place which I call monolithic hell. Any kind of development, testing, deployment of that application becomes incredibly slow and painful. So this model that comes with this wonderfully simple transaction mechanism sort of breaks down. And that's kind of the big motivation for the microservice architecture, right? Instead of building something that is way too complex for us to sort of develop, test, deploy, etc., we just functionally decompose it into a set of loosely coupled services. And the services themselves are simpler. Each one contains, code that can still fit in a developer's head. And we can, everything about it has become, many aspects about the microservice architecture become a lot easier. Among other things, it lets us parallelize software development. You have a team working on each service, and they can develop and deploy and so on in parallel. So one team's working on a customer service, another team's working on an order service, and so on. And it also lets you adopt new technology much more easily. Each service can use a newer, better technology stack. So there's a whole bunch of sort of drawbacks that, basically you end up outgrowing your monolithic architecture, and there's a whole bunch of benefits with adopting the microservice architecture. But, there are no silver bullets, and as you're going to see, there's some issues with transaction management that cause some really interesting challenges in the microservice architecture. So anyway, if we were to apply the microservice architecture to our online store, we'd have something that looked like this, right? Bunch of services, customer service, order service, and so on. Sitting in front of that would be an API gateway that's doing request routing and API composition and so on. So that's all pretty good. But there's this interesting characteristic, namely that each service has its own database, or at least its own private data. There might just be one database server, I suppose, but within that server, each service has its own private schema or private tables. Now, the actual details don't matter. But this notion of having encapsulated data is really central to the microservice architecture, because if services communicate via the database, they are no longer loosely coupled. A classic example, right, is, so imagine that you're working on the order service and you want to change the schema. If you're the only one accessing it, it's really simple, right? But if there are 5 other services and 5 other teams who are accessing your table, you're going to be in meetings for a really long time, right? Coordinating exactly when you can make those changes and how they can adapt their application to fit, to the point where it really gets in the way basically the amount of coordination and the communication that's involved in order to change the schema just slows you down and defeats the purpose of having the microservice architecture in the first place. The whole goal is, parallel development by autonomous teams, and as soon as you share data, you're no longer autonomous. You're tightly coupled and slowed down. So the only way services can access one another's data is through APIs. But then the question is, well, how do we maintain data consistency? Because I've broken apart the data, yet there are still requirements for transactions, like the one that I just showed for doing the credit check when placing a new order that will span multiple services. So if we revisit that SQL that I just showed, right, classic simple set of SQL statements, in a microservice architecture, this is really problematic because orders belong to one service, customers belong to another. So that's not going to work, unless we had some form of distributed transaction. So, it's sort of a bunch of problems, but in theory, you could use some form of sort of two-phase commit or distributed transaction management mechanism that spans multiple services. But it turns out that distributed transactions, although they work, have pretty much fallen out of favor. Just sort of modern applications simply don't use distributed transactions anymore. There's sort of a whole bunch of problems, with sort of distributed transactions, coordinators, sort of the single point of failure, potentially chatty with all the messages. There's potentially locks are being held. So in theory, it sounds great. There's also a bunch of fine print about what kind of isolation levels you get with distributed transactions as well. And then there's this sort of really minor detail, namely that many modern technologies like NoSQL databases and modern message brokers actually don't even support distributed transactions. So even if you wanted to use it, you could not. And then there's the CAP theorem that basically says you have to pick between consistency and availability, and people prefer availability. So it's sort of like, oh, this two-phase commit thing's not an option. So in order to maintain data consistency across a bunch of services, we actually need to do something different. And that's where this saga mechanism comes into. It's sort of the new transaction model when you have transactions that span multiple services. So the big idea is really sort of simple. So instead of having a distributed transaction that spans a bunch of services, you use a saga that is a sequence of local transactions. So in this case, instead of a transaction spanning 3 services, A, B, and C, you have a saga, and there's a sequence of 3 local transactions, one in A, one in B, one in C. And this, as I mentioned, this concept was introduced back in 1987 by a paper. And actually, their motivations were somewhat different. It was sort of like, well, if we have these long-running transactions, they're going to hold resources and locks and for a long, long time, and it's going to have terrible sort of consequences for the behavior of the system. So let's break it up into a set of shorter transactions. And so this is kind of the concept of a saga adapted to a slightly different scenario, but to sort of address sort of different but very related concerns. So the way this would work in the case of creating an order is as follows. So, a request comes in to create an order. That would be the first step of the saga. It creates an order. And then somehow, once that has completed, the next step is triggered. And so a transaction will then occur in the customer service, in this case, it will attempt to reserve credit. So, an order gets placed for, £100,000. The reserve credit operation will then be performed in the customer service to try and reserve that much of the users, of the customer's available credit. And then when that has completed, another transaction takes place back in the order service to then either approve the order if there was sufficient credit or reject the order if there wasn't enough credit. So we sort of change things slightly. We're creating the order and then verifying that we can actually kind of go ahead with the order. And as you'll see, that has some implications in a little while about sort of API and design and so on. But that's the idea. I mean, there's obviously there's some interesting details, like what do those arrows mean? How does the completion of one step trigger the next step in the saga? And I'm going to get to that in a little while, about this whole saga coordination mechanism. But that's the general idea. Break up a distributed transaction into a set of local transactions, or sequence of local transactions, because they have to be ordered. But there are a few complications with this model. Namely, first complication is, what do you do about rollbacks? You think about an ACID transaction, you can make arbitrary changes to the database, and then at some point decide that, I'm about to violate a business rule, and you can just abort the transaction, and everything that you have done just sort of magically gets undone. But in this model, each of the local transactions is committing changes, and so you could be 10 steps in and decide that you have to roll back, except that there's no automatic rollback, and you have to explicitly undo what you have done previously. So there's this whole notion of compensating transactions. So it's sort of, conceptually, this kind of comes from the original paper. You have, the sort of the forward transactions are called T. So you got T1, T2, T3, T4, and so on. So those are sort of the success cases, or the success steps. So conceptually, every one of those forward transactions has a corresponding compensating transaction that undoes what it did. So that's kind of going forward, and then these are the undos. So then that means, let's imagine that step T2 fails, well, you have to undo step T1, and so you execute its compensating transaction. So you kind of go forward as far, and then you do n steps forward, and then if the n plus 1th step fails, you then have to undo the preceding n steps. But you have to program this. This is, unlike with ACID transactions, this no longer happens automatically. So that's a bit of a complication. You actually have to think about kind of all the possible scenarios and actually how to undo them. In the case of reserving credit or creating an order, it's pretty straightforward. If the attempt to reserve credit fails, you just reject the order. So you create the order. I guess strictly speaking, you could delete it, but that would be weird. So you mark it as having been rejected due to insufficient credit. So that's not too complicated. If you think about what a bank would do, apologies to anyone who actually works at a bank, because I have no idea what they really do. But imagine that you're transferring money between two accounts, right? You debit the from account, and then when it's time to credit the to account, as sort of step 2 of the saga, you find that the to account has been closed. So you then have to undo the debit, which in this scenario would mean doing a credit. So the customer would see 2 transactions on their bank statement. Interestingly, at that point, you might discover that the from account has been closed, and so you're sort of in this weird limbo where you can't actually credit the to account, and you can't undo the debit of the from account. So, some whatever business process, higher level business process has to be kind of kick off at that point. So there's a whole bunch of scenarios that you have to think through in order to come up with these various compensating transactions. So that's one challenge. Another challenge is, this actually complicates or potentially complicates the design of the API. The request initiates the saga. And then the question is, well, at which point do you send back a response? And there's really 2 options. So one option is that you could not say it's HTTP. You don't send back the HTTP response until the saga has completed. Now, the good news is that even though we're sending messages around, the latency is likely to be, pretty low. So the response is likely to come back really, really quickly. This is nice because you haven't changed the semantics of the API the fact that the implementation is asynchronous has no bearing on the API. The downside is that this kind of design reduces availability, because in order for the response to be sent back, all of the participants need to be up, especially the service that's sitting there waiting for this to complete before it can send back an HTTP response. So the availability of this approach is sort of theoretically less. So another option, which in some ways is preferred, is to return a response back to the client as soon as you've created the saga. Now, and that's nice because the client gets a response, so it gets the order ID, and you're no longer dependent on all of the other components of the system being available, or being even, they don't have to be up, they don't have to be capable of responding in a timely way. That order will still get verified. The complication, of course, is that you're telling the client that, say in this case, the order has been accepted, or at least been created, but we can't really tell you whether we're going to allow this order or not. And the client is going to have to poll to see the order status. Or maybe you could use some event-based mechanism to tell the client that their order has been processed. But interestingly, I think from a sort of system design point of view, option number 2 is somewhat preferable, right? You just want to have loosely coupled, highly available systems. So in the case of orders, I could say, create order. We'll create an order, and kick off this saga, gives you back an order ID, but doesn't really make any strong guarantees about the state of the order at that point. It hasn't been fully validated, and the client would have to call the get order API in order to find out the final outcome of that order. But that's sort of a nice from a sort of highly available design perspective. But it complicates the client. Doesn't necessarily have any impact on the user experience, right? Especially if you're building a rich client using Angular or React or whatever the fashionable JavaScript framework is, you can hide all of this from the user. Among other things, provided that something completes within 100 milliseconds, because our brains are so slow, it will actually appear instantaneous anyway. And even if it does take longer, you can just display a dialog box, pop-up that just says, like when you're placing a credit, it's charging your credit card, right? It says, this might take up to 30 seconds, don't press the back button or something like that, right? So you can communicate that, the system is processing your order. In a nice case, the server can use WebSockets to push a notification down to the UI. So there's some interesting issues there. But it's the UI, the APIs might be a little different, a bit more asynchronous, but the UI, the user experience can be the same. The other issue is that the business logic is a little bit more complicated for a similar reason. Right? Each step of the saga commits its changes, and that means that other transactions will see data that's sort of in this inconsistent state. So whereas before, an order just appeared in the system in an approved or let's say in an approved state, right? Now there's this more complex state model where the order is in this pending state. And that means some other transaction has to know what to do with that order when it's in that state, which just means that your business logic is a bit more complicated, right? So for instance, like if the UI is hiding this, it's a little different, but let's imagine that the order gets created, then immediately a request comes in to cancel that order. You're now in the situation where the order is in a pending state, and what does it mean to cancel the pending order? Because, there's this saga that's going off and actually interacting with other components of the system. So canceling is a little complicated at this point. Do you somehow interrupt the existing saga and tell it to give up somehow? Well, maybe. Or does the cancel operation wait for the create order saga to complete and then go and cancel the order? So there's some really interesting design issues around that sort of arise from the fact that this inconsistent data is actually exposed to other transactions while sagas are completing. Once again, I think it's doable, but there's some challenges. Okay, so that's kind of the introduction to sagas. Next thing I want to talk about is sort of the coordination mechanism. So far I've drawn sagas as sort of a bunch of boxes with arrows between them. And now it's sort of time to talk about the nature of those arrows, right? So the idea is that when one saga step completes, one of these TIs completes, some piece of code has to run to figure out what to do next. So if that saga step was successful, which of the next steps to execute? Because there might be some sort of branching model. Or conversely, if there's a failure step, how to undo what's been done so far. And there's two different models. One of them is choreography, where the saga participants sort of figure out what to do amongst themselves. And then there's an orchestration model, which is where there's a centralized component that's deciding what to do next, saga orchestrator. So in theory, if you look at choreography, there's some code running in each service that sort of figures out what to do next. So in theory, the order service, after it's done one thing, tells the customer service to do something, and then the customer service tells the order service. So this sort of logic is like about this particular saga is scattered throughout the system. Arguably, you could do it that way, but it kind of couples things together. So sort of a nicer, I think a cleaner model is to really have some centralized decision-making component. So you can imagine that there is something called a conceptually at least, a component corresponding to the saga telling the participants what to do. So, and I'll sort of show more details of that in a minute. But it's nice because in a way the components, the services are no longer sort of tied in with the sagas themselves. So this actual coordinator component, you can kind of model it as a state machine. So this is like classic UML state machine model. So, when the saga is created, it performs an action. In this case, it's telling the customer service to reserve credit, and then it's in the reserving credit state waiting for the response to come back. And then if the credit's reserved, it tells the order that it's approved. If the credit limit is exceeded, it tells the order to reject itself. And then the saga transitions to either the approved or rejected state. So these coordinators are like little state machines that respond to, they send out commands, they invoke the saga participants, and then when the response comes back, they transition to the next state. So it's a nice simple model. We can code those up in a straightforward way. But there's two different models. One is what I'm calling the implicit orchestrator, where you're using an existing domain model to sort of orchestrate the saga. And you're going to see an example of how the order can kind of drive the whole drive the saga mechanism. That's kind of nice because you're just leveraging an existing class. The downside is that the order is doing what it has to do, plus this coordination responsibility. Or, as I kind of hinted in the picture, you have a separate object that's solely responsible for orchestrating a single saga. And that's kind of nice. It's much better separation of concerns, but where you've got another component in the system. So this is an example that I've used a lot in a talk on event sourcing that's a related sort of very tightly related to this saga mechanism. And that's where the order is responsible for coordinating its own validation. So in this model, which is very event-based, an order is created and it emits an event saying, I've been created. And then the customer service will get that event, reserve credit, emit events indicate the outcome of the credit reservation, and which then causes the order via its event handler to change its state. And in this case, the order is basically acting as this little state machine, interacting in this case, it's just with the customer service, but you could imagine that if there was an inventory service in there as well, the order would be waiting for the inventory reserved event to come back from the inventory service as well. So this works pretty well, except that, the order's kind of got overloaded responsibilities. And there's sort of some other subtle issues around cyclic dependencies, because services are consuming one another's events, which gets a little, it works, but you hate cyclic dependencies. So another approach is to have an explicit coordinator object, which I sort of just refer to as the saga, even though sort of it's kind of the saga is its more general thing, but I call them sagas. So in this case, request comes in to create an order. The create order saga is created, and that actually immediately turns around and creates the order. So we've got this order in existence. And then the create order saga tells the customer service to reserve credit, which it does, and then it sends back a reply, and then the create order saga then approves the order. So in a more complex use case, this create order saga is telling like 5 different services, one after the other, what to do. So it's sort of much more complex state machine model. So that's kind of this notion of an explicit saga orchestrator. Got a little bit of code. So this is very much work in progress. I hope to open source this really, really soon, probably during a plane flight over the next few days. So this is the saga framework. So the create order saga implements some interface. And the saga itself is purely behavior. It's this stateless singleton. And actually in the Spring version, it's just a Spring bean. And the state is separate. And the state is comprised of 2 things. One of which is an enum, whose values represent the actual states of the state machine. And then there's a data object that has the persistent data for this saga. So it's important to remember the saga is this object that resides in the database, because it's this long-lived thing. So that's kind of at an abstract level. You've got this enum and a data object, and together they define the state of your saga. And then in terms of the code, the critical part is the definition of the state machine. So I'm working on this simple little DSL for describing a state machine. So it specifies like the initial method, like what method to invoke when this saga is created. So that's the initialize method. And then for each one of the states, how to react to replies coming back from whatever participant got sent a response or got sent a request. So here it's saying, if we when we're in the reserving credit state and a reply comes back from telling the customer service to reserve credit, if it's successful, invoke handle credit reserved. Otherwise, if it's unsuccessful, invoke handle credit limit exceeded. So it's just declaratively specifying what the state machine model is. And then if you look at the initialization model, it's actually it's creating the order. It's actually initializing its data object, actually putting the order ID into it. And then it's sending a command, or it keeps sending a command. I haven't actually said that it's using messaging yet, but it actually uses messaging. It sends a command to the customer service proxy. So it's like reserving credit at this point. So that's that's the initialization method. And then the corresponding method that handles a successful outcome just updates the order to say, oh, the credit has been reserved, and then it changes the state of the saga to be approved, at which point it's done. So simple state machine with various transition handlers that either, in this case, update the order domain object, as well as updating the state of the saga. And then on the customer side, there's a command handler that gets invoked in response to receiving the reserve credit command, and that just retrieves the customer from the database and invokes the reserve credit method. And this is some annotations to say where to send back the reply to. As I've hinted, this is underlying all of this is some messaging infrastructure. So that's the kind of code that you write to orchestrate this. So it's fairly sort of simple, mostly declarative, kind of a little state machine that's telling various services what to do. Then the underlying mechanism for this is what I'm calling transactional messaging. So if you think about what's going on, right, the orchestrator has to tell the participants what to do. The participants have to reply and send back a message. And all of this has to be reliable, right? the presence of transient failures of any of the participants, right? Like in the same way that we rely on database transactions to sort of, be 100% reliable, this transaction model also has to be reliable. And a lot of that comes down to the particular communication mechanism that's used between the participants. And it turns out that if you just think this through, the only thing that really makes sense is to use some form of asynchronous messaging. Using REST or some other RPC approach just doesn't give you the right kinds of guarantees, right? Because the nice thing about messaging is you send a message, you give a message to the message broker, and assuming that the message broker has durable at least once delivery, that message broker will deliver that message eventually, right? And you don't have those kinds of guarantees with REST, right? Both clients, both ends have to be up at the same time, and there's a whole bunch of issues around guaranteeing that things really happen. So underlying this are a bunch of message channels. So every saga participant, like the customer service, has a command channel, and so the customer service is reading commands from that channel, processing them, and then sending back replies. And then obviously the saga orchestrator has to just know, I want to invoke service XYZ. I have to send a command to that service's command channel, and then then it needs to read the replies from that participant's reply channel. So in the case of the order service, customer service example, looks like this, where we've got in the message broker, the customer service has a request channel and a reply channel. And so the commands flow from here through that to this, where they're processed, and then the replies flow in the inverse direction, back to the saga orchestrator. So at some level, it's just simple messaging underneath, but there is this kind of complication, namely that the message sending and actual receiving and processing all has to be transactional, right? So the actual, so for instance, if you were to commit a transaction and then send the message, there's always a risk that you could crash in between, right? Right after committing the transaction and sending the message. And if you tried to send messages inside a transaction, or if you sent a message inside the transaction, you could crash, or the transaction could get rolled back, and you've now, in either case, you've got this sort of broken behavior. So basically, sending a message and updating the database has to be this atomic transactional thing. And ironically, if you were using sort of traditional Java EE technology, that would mean using JTA plus JMS plus JDBC to make sure that would happen, right? But this is exactly the kind of technology that we're trying to avoid at this point. So we're using sagas to avoid 2PC, so we can't use 2PC as part of the implementation of a saga. So the good thing is that this is not too challenging to solve. And the trick is to use a database table as a temporary message queue. So when some service that wants to send messages is updating its data, so the customer service or the order service, as part of that local ACID transaction, it inserts the message into the message table. And because that's all local ACID, that's guaranteed to work, right? So we just got, so step number one, get puts a message in sort of this outbox table. You can think of it as a set of messages that we need to send, these messages that we need to publish to a message broker. And so that's all wonderfully atomic. So the only question is, how do we get the messages, out of that database table and into the message broker? And it turns out that there's actually a couple of different options. So in theory, you could poll, right? Periodically, the message publisher just issues a select star from messages table. The interesting thing is what the where clause is, right? Like how to identify new messages. And one option actually is to just delete them after you've sent them. So in theory, you could just periodically poll, and this works reasonably well at high scale, at low scale. There's sort of potential latency issues and so on, and performance-related issues. And if you're not deleting messages out of the message table, then keeping track of which messages are new is actually remarkably tricky. Because say if you could have multiple transactions that are, say, generating message IDs, so they can actually commit in a different order. So transaction A could generate message ID 4, transaction B could generate message ID 5, but transaction B could commit before A does, so message number 5 will appear in the database before message number 4. And if the polling mechanism is keeping track of the highest messaging ID that it's seen, it could actually skip over messages. So it's a really irritating little problem. So this approach has issues. So another option which is sort of my preferred one, though there's some tricky issues with that, is to actually tail the database transaction log or commit log. So you think about how relational databases work, or most databases. Changes get written to a commit log and then applied to the data tables, right? So if you just monitor the transaction log or commit log, depending on what it's called, you will see all changes to the event or to the message table, and you can then publish them to a message broker. And this works pretty well. I mean, the only complication is that the actual mechanism on how you do this is very, very database specific. So like, system I'm working on, it uses MySQL, and you can just plug into the MySQL master-slave binlog replication mechanism to see these changes. It's fairly straightforward. DynamoDB has tables have streams. MongoDB has the oplog, and so it goes on. But it's very, very database specific, and not universally supported. But it's kind of a very straightforward mechanism. So that's it's kind of like you've got the saga mechanism, and underneath that is transactional mechanism, is the transactional messaging mechanism, and supporting that is some form of transaction log tailing to get the messages into out of the database into a message broker. So that's kind of sort of pretty much it for my talk, which is good because I only have 3 minutes remaining, right? So kind of the key points are, right, so having a database per service, or in other words, encapsulated data, is really important in a microservice architecture to ensure that the services are loosely coupled. You can't use two-phase commit as the inter-service transaction mechanism, and instead you want to use sagas. And then underlying the saga mechanism is some form of transactional messaging system in order to make this execution of the sagas completely reliable. So that's my talk. Thank you for listening, and here's all my contact info and everything. So I hope that you found this useful. So thank you.